Work it, make it, do it, make sense.
Okay. Is everybody having a good Friday afternoon at Devox? Yeah. Excellent. Hands up if you already know a fair amount about cryptocurrency or describe yourself as an expert. One person. Okay, that's good. Don't kill me for anything I'm about to say. Beat me up in the bar afterwards. Okay, so this talk is called Building Smart Contracts on the JVM, and it's really the result of some research that I did last summer for a company called R3. So there's a bunch of links at the end which explain where to get more material. There's a lot in here, and I've only got 15 minutes, so I'm probably going to talk quite quickly. So I'm Ben Evans, and I've done a bunch of stuff in the community, Java champion. I serve on the Java Community Process Executive Committee, which is the body which determines new Java standards. You might have seen some stuff in the tech press about Java 9 modules. Yeah, that's been occupying a lot of my time lately, so if you want to know about that at the end, come and see me. Career-wise, I've spent most of my time in banks. I founded a startup called JClarity. I was chief architect for listed derivatives at Deutsche Bank, and before that Morgan Stanley. So I've seen quite a few financial systems, and I'm interested in cryptocurrency really from both the technical and from the financial point of view. I don't think necessarily that they're going to be the thing which changes the finance system as we know it, but there is certainly some fascinating computer science aspects in there, and that's kind of how I got involved in this project. So what are we going to talk about today? Well, we will talk about cryptocurrencies briefly because some background and a primer is needed, but it's the computer science aspects that I really want to focus on. Then I'll talk about the JVM and how that fits into the picture and why the JVM might be a good platform for building cryptocurrencies on and why it might be a bad platform as well. As you probably won't be surprised to discover, I eventually concluded that it was a good place for cryptocurrencies and smart contracts. So after that, I shall go deeper into the technical work. We are going to see some bytecode. We are going to look at class loading. And the bottom two bullet points here are really what the whole talk is building towards. I'm actually going to talk about provably deterministic execution, programs that will not run if they are not deterministic. That's ultimately where we're going to end up. And probably some of you are thinking, hold on a minute, I did a computer science degree, what about the halting problem? Well, hold those questions to the end, please, because we are tight on time. Okay, so let's go. First of all, let's talk about cryptocurrencies. And let's also talk about some computer science along the way. So the best known of all cryptocurrencies is, of course, the fantastic Bitcoin, which everyone knows all about, partially because of its high-profile role in ransomware, scams, drug dealing, and other forms of illicit activity. And if you're a student of human folly, as I very much am, Bitcoin is very attractive because you can see the absolute best and worst of humanity, often side by side, if you spend any time lurking in the Bitcoin community. Ultimately, what it's supposed to be is a digital form of cash, and that's quite interesting because if we think about what properties cash has and what properties, therefore, that we would want online cash or digital cash to have, we might end up with a list which looks something like this, because physical cash has all of these attributes. You can't duplicate it. If I spend a £10 note, I can't create another one, which of course for digital patterns of bits is trivial to do. So the lack of not being able to duplicate it immediately indicates that whatever form digital cash takes, it's not a pattern of bits. It has to be something else. What else would we want cash to have? Well, cash is anonymous. If I go to a bar and buy a beer, I don't need to know who the barman is, and he doesn't need to know who I am. I pay with cash, and there's really no record of the transaction. And Bitcoin doesn't really do that. It's really pseudonymous rather than anonymous, but that distinction would probably take us too far afield for 50 minutes. But we would kind of want a level of anonymity to be associated with our cash. It should be fungible and liquid, by which I mean it should be exchangeable for any form of goods and services, and it should be readily accepted. If it's network-based, then the network has to be fault-tolerant. This stuff has to work. It's going to be used for transactions for essentially all of human behavior, so the network had better work. And transactions potentially even at a distance between parties that don't know each other and who may not trust each other. And that's also an interesting problem to solve. The trustlessness, if you like, if the network would also be important. And finally, the network should be unable to prevent anyone from using it. And that's kind of an interesting point as well, because having read this list, there's something which might not ever have occurred to you. Cash has these properties, but your debit card doesn't. Your debit card has precisely none of these properties. And what's actually happened is that we already have a dual financial system. We have the financial system which is represented by cash, which has these properties, and we have the banking system, which is actually a private network. And all that happens is that the units of currency which are used in the private banking network happen to be the same as those of cash. And at the end of each day, all banks essentially tally up who owes what to whom and perform a large settlement between each other as to where the actual real money, the cash, should be moved around to. So we're already using a system which is like digital money, and so much so, in fact, that most of us who haven't stopped to think about this might have confused it for being the same as the actual cash that we have in our pockets. But they are, in fact, very different things. So let's move on. Let's look at what crypto might be able to do to help us. And Bitcoin basically manages to solve a surprising number of these problems. The Bitcoin approach is that it's resistant to double spending. It does have a measure of anonymity, although as the saying goes, if your threat model includes the NSA or the Mossad, you have bigger problems. I am perfectly sure that the NSA either knows or could find out if they chose to who owns every single Bitcoin on the planet. But the network itself is at least pseudonymous. There's an interesting paper released a few months ago where someone did an analysis of the Bitcoin ledger and was able to map about a sixth of all Bitcoins in existence to either an email address or to a username on a social media network, which is kind of scary, because for something that's supposed to be anonymous and largely used for illicit stuff, a simple network analysis leading to 1/6 of the ownership being revealed is a fairly bad flaw. Anyhow, so that's why one of the reasons why I use the word pseudonymous rather than anonymous. And Bitcoin is of course trustless as well. This quote by Richard Kendall Brown, I think, is quite telling. It's about transferring value at a distance without a central third party. I mean, it's a slightly flawed quote, and I can see a couple of things that are wrong with it or I could nitpick about, but it broadly gives the sense of what Bitcoin has managed to achieve. Okay, so that's the background of our cryptocurrencies. The computer science aspects of crypto and of Bitcoin are really what interests me, and there are really four pieces of separate, interesting computer science that are buried just beneath the surface of cryptocurrencies. There's hashing, and its use in producing the chain of transaction blocks, the dreaded blockchain that we've heard so much about in the height phase of the tech press. There's also what's called the Byzantine generals problem. This basically is how do you reconcile the fact that your network may have bad actors in it. Another classic computer science problem. The names of so many greats of computer science, Leslie Lamport, Barbara Liskov, and so many others are attached to the Byzantine generals problem. And for those of you who are students or aficionados of computing history, studying the history of just that single problem will show you a great deal about the history of the field. All of which would be absolutely fascinating to talk about this afternoon. Unfortunately, I only have 50 minutes, so I'm going to focus on just one of these, and that's the Turing completeness of smart contracts. Now, hands up if you know what a Turing machine is. Excellent. So you recall back in the dim and distant hungover days of first-year computer science that you have a machine which has a tape, and it basically is equivalent to programs. And basically, what we probably remember of the halting problem is that it's not possible to construct a general algorithm which, given any possible unknown program that the algorithm will tell you correctly whether or not the program will terminate. Okay, so great, halting problem. What does that have to do with crypto? What does that have to do with smart contracts? Well, a smart contract is a program which runs on top of a digital distributed ledger like Bitcoin. Okay, because that's really what we're talking about. Rather than a pattern of bits, which of course could be duplicated, we want to model something which looks like the private banking system, which we have been so unconsciously using all this time. And what that means is that we are going to have the equivalent of bank accounts or Bitcoin addresses, which have amounts attached to them, and we're going to be able to write a program which indicates how to manage the assets which are recorded in the ledger. So, do we want this language to be Turing complete or not? Now, obviously, the class of what you can do in non-Turing complete languages is rather restricted and rather boring. So we probably do want full complexity of Turing completeness. But then, of course, the problem is we're running this on top of a ledger which contains people we potentially don't trust. We're really going to start running code from an unknown, untrusted origin in a network which almost certainly has adversaries in it? Well, that's not sounding good either. So what are we going to do? Well, let's pause and let's have a think about the JVM and see if there's an angle here which we can use to address the problem. Well, Java is 21 now. He's finally old enough to drink in the US. So people who've been telling me for years that this picture actually shows Duke with some kind of frothy coffee or something, it's clearly wrong. He's clearly now old enough to have beer. So Java is 20 years. It's been enormously successful. I'm not going to tell you that Java is the mythical perfect programming language. Of course it's not. But languages which make it to 20 generally have something of a story to tell about them. And I think there are two quotes about Java which particularly stick with me, both from James Gosling, the originator. Firstly, Java is a blue-collar language. This is the single biggest and most important thing which explains the design decisions in Java, the language. It is designed for working programmers. It is designed for people who get their job done and deliver fairly mainstream business applications. It's designed to be stable and robust, small c conservative in its design choices. And James has also said, the other quote which I thought about putting on this slide, that if he didn't know the right way to implement a feature in the language, he would rather leave it out and wait until he was sure. So you can complain about backwards compatibility, you can complain about the rate of change of Java, but this is not an accident, and it's not because the people who maintain and shepherd the language are incompetent. Quite the reverse. It's that they take their responsibilities for the language extremely seriously. And you can see that that much as we as developers might want, lambdas 10 years ago or whatever, for many business applications, backwards compatibility and the stability is a huge strength. Now, the second quote is really about the language itself. Java is a very simple language. In fact, here it all is. 53 keywords, no more. When I gave this talk to a bunch of C++ developers, an argument broke out in the room amongst the C++ developers about how many keywords in C++ there actually are. We got up to about 200, I think, and then they started arguing amongst themselves. So that was quite disruptive. That talk did not fit in 50 minutes, but we finally got it calmed down. But in Java, we only have 53. Notice that there are two keywords that none of you, not a single person in this room, has ever used. Goto and const. Both are reserved words in Java, and both are illegal, and the compiler will reject any file which tries to use them. They are reserved for future use. Good luck with that. There are, of course, other keywords here which you may never have used or shouldn't use. Assert, for example. But we'll come back to some of those stranger keywords in a bit. So the language is extremely simple. And the operating environment is also quite well engineered and also quite simple. We have a clear separation of the concern of compilation, generation of a class file. We have the class loader, which we're going to talk a lot about, which actually is where a lot of Java's security model is implemented, and that's going to be a very important thing to us. And then we have the method cache, an interpreter, which is defined by a very clear standard, the VM spec, and then also some Jit compilation. The only real major subsystem of the JVM that's missing from this diagram is, of course, garbage collection, but that's an operational concern rather than specifically a design one for our purposes. And I like to think that this represents a very clean and clear separation of concerns. And I was trying to think about a way to explain the concept of separation of concerns to some junior grads who had never come across the term before. And then I found this. Next time you have to explain what a separation of concerns is, show them this picture. Okay, so this is starting to sound like we might actually have some good traction with Java. Java might be a good language for building smart contracts. What are our key positives? Well, Java is extremely well understood and it's extremely tractable. It has been around for 20 years. It has been studied by literally millions of people worldwide. The semantics of bytecode are fully understood. The security model has been attacked over and over again, and although there have been implementation bugs, there are always implementation bugs, the model itself has withstood 20 years of serious efforts to break it, and it's held up. So we have a very mature environment. There's also a lovely tooling space for JVM bytecode with a lot of libraries and a lot of good tools out there. And we also have the class loading pinch point. Now this is integral to the security model, but it provides us with not only the existing security that the platform comes with, but because class loading is a hook that developers can access, we can use it to apply additional security concerns. And remember, we're driving towards rejecting non-deterministic programs. We can do that at class loading time, and that's actually going to be one of the keys to getting this to work. Okay, sounds great. What's the catch? Well, Java is highly dynamic, and it is essentially multi-threaded. All Java programs, more or less, are multi-threaded. Even if your code isn't, the JVM is. And that's, it was the first mainstream language to provide threading, and all multi-threaded programs are unfortunately non-deterministic. So that sounds almost like it should be a showstopper. But it turns out that the interpreter spec allows, if you are a single-threaded application, to produce deterministic answers. Okay, now it won't work for things like which depend upon the actual running time of the program, because garbage collection could happen, for example, and you could get non-determinism that way. But aside from that, as long as you don't depend on external clock time, which you can't anyway, because if you want to be deterministic, the last thing you should be doing is calling something like system.currentTime millis, because it will give you a different answer each time you call it. So maybe the fact that we can't depend upon external wall clock time isn't a problem. So in a single-threaded program, maybe it will be okay. Okay, well, what about Jit compilation? Well, here's the thing about Jit. If you have a Jit compiler, you must, to be compliant, have the same semantics as interpreted code. So even the fact that the Jit compiler is non-deterministic, and by the way, it is very non-deterministic, you will get a different set of compiled methods, Jit compiled methods, for every run that you do of every Java program you execute. The set of methods is not stable from run to run, even in highly controlled performance environments. So again, that looks like it could be a showstopper, but in fact, we're saved by the fact that the Jit compiled code has to have the same semantics, and once again, we're not depending on external time. So it looks like we might actually have a shot at making this work. So let's see how we're going to do it. Well, let's bluff our way through some bytecode. Here's a class file. If you like editing hex directly, which I do, this is hexed 0xed, which I think I secretly like because it's a terrible Unix joke in at least 2 different ways at once. So that's going to make it appeal to me. What can we see here? Well, we can see the pure hex view of the class. We can see on the right-hand side some stuff which has got strings in it. That's the area of the class file called the constant pool. And most of it is going to be taken up with the bytecode of the methods. So bytecode, if we recall, is called bytecode because each operation or each opcode is represented by 1 byte, potentially with some parameters following it in the byte stream. It's big endian, for those of you that have read Gulliver's Travels, you know where that comes from. There are 256 possible bytecodes, because 1 byte, and there are about 200 in use. And if that sounds like a lot, it's not because there are 200 different fundamental operations that the bytecode can do, it's because bytecode is typed. So the same general operation will have 1 bytecode used for objects, one bytecode for floats perhaps, 1 for ints, and so on. So each of the primitive types potentially can be represented on a particular bytecode family. Bytecode is an abstract representation. It is not machine code for an imaginary CPU. Hands up if you were told that at university. Good. I'm glad that myth has finally died. When I first learnt it in 1998, I think that myth was still very much alive. Bytecode is stack-based. So what I mean by that is that the execution has no registers. So everything which you do, when you call a Java method, a new stack is generated, which you load things onto and then operate on the top of the stack, consuming entries from the stack and replacing them with any results of the operations. So that's different from a call stack. So I'll sometimes use the expressions evaluation stack and call stack. Bytecode is not really a compiled form. JavaC, to me, is not really a compiler. For those of you who remember your compilers courses, it's really the front half of a compiler. The thing which actually produces the machine code, the real meat of the compiler, is the Jit compiler. So when I say compiled, I always mean the Jit. I don't mean JavaC. Okay, let's see some bytecodes. So let's look at a few forms. So, as promised, we've got dload to load doubles onto the stack. A-store means store the object in an appropriate local variable. I'm just going to do enough of the bytecodes for the rest of the talk. There are others which occasionally crop up. Bytecode is actually pretty easy to read. There's a tool called JavaP, which will dump out bytecode and let you read what's inside files. And once you get the hang of it, well, for Java, the bytecode that's produced is extremely similar to the Java language code, once you've taken into account the fact that you're actually working on a stack machine. Other languages that's not the case. So the Scala compiler produces reams and reams and reams more bytecode than JavaC does, and it does some really quite amazingly clever, possibly too clever, things under the hood. Okay, so here are our load and store opcodes. These basically are going to put things to and from the stack. The way to read these, it's dead easy. The family name is here. It may need a prefix, like load, for example. The arguments basically say how many other bytes of argument it takes. Round brackets means they're potentially optional for some forms of the bytecode. The stack layout column basically tells you what the effect of the opcode on the stack is. So, for example, if you started with an empty stack and did an A load, you will get one thing on the top of the stack after the opcode is finished. You have load and store, you have get field and put field. These obviously are going to store things not in local variables, but in the fields of this object, or potentially another object if for some crazy reason you have public fields, which none of you do, right? Arithmetic, so none of these opcodes take any kind of argument. They all operate on the two things which are on the stack. And here is where a piece of the security model comes into play. Suppose I load an object onto the top of the stack with an A load, and then I load an integer, an int, sorry, onto the stack. And then I issue an I add. What am I trying to do? So I've loaded an object, I'm loading an int, and then I issue an I add instruction. And then return that as an object. Absolutely, it's pointer arithmetic, and it's completely disallowed. So when the class loader sees that sequence of bytecodes, it's immediately going to reject loading that class. Now, of course, the Java compiler, JavaC, will never emit such a stream of instructions, but I might be able to handcraft it if I was sufficiently devious. But it doesn't matter because the security model and the class loader will protect us. Float control. Java bytecode only has two legal float control arguments these days. It's if and go to. That's it. There were, at one stage, others. JSR and RET produced a kind of a local subroutine effect, but they were disallowed in, I think, Java 6. I think any class files which are Java 6 or later will be rejected if they contain JSR and ret. Table switch and lookup switch, they're sometimes seen for the output for what switch statements have been boiled down to. But mostly it's just if and goto. Notice that goto can only jump within the local method. So again, the class loader will check and says the target of your gotos, is it in this method, or are you trying to branch outside of the method? Oh, you are. Well, guess who's not getting loaded today? The invocation instructions, again, this is the starting point for so much that we could talk about here, but the key thing to note is that they are the only way that you can call another method. If there's no goto instruction which will take you outside of the current method, if you want to genuinely call another method, you have to use an invoke. So what this means is that the JVM is also immune to a whole class of attacks that would be possible in sort of late 90s, early 2000s C. The kind of attacks where you use an array to write out some actual machine instructions, overwrite the return address of the stack, and jump into the code that you just wrote out. That doesn't work in Java, because fundamentally, goto is local to a method, and the only way to call a method is by an invoke. So what I'm saying is that the Java platform always knows the difference between bytecode and data. That's kind of a useful property for a security system, or the basis for a secure system to have, right? A couple of other ones we need to know about. New, which allocates memory. So basically, as we'll see, a Java object construction boils down into two separate operations. A new opcode for allocating the memory, and an execution of the constructor body. We also have monitor enter and monitor exit. Which Java keyword do you think those have come from? Yeah, synchronized, that's right. So we'll have something to say about those as well. Okay, very quick example. Here is the world's most interesting class. It has one field on it, and it's an int, and a getter and a setter. Disassemble the bytecode, we end up with something like this. Basically, there are three methods here. We only talked about two here, so sure enough, just as you were always taught, the compiler has inserted a constructor for you. And notice what it does, it calls object init, which is necessary. Objects which are constructed and which don't end up calling object init are actually illegal on the platform. Bad things would happen if each object doesn't at some point go through the object init constructor. Okay, so let's look at the methods one at a time. Let's start with the getter. So, little tiny bit of code. A load 0, what do we think that does? It's going to load something onto the top of the stack. What is it? An object. The A prefix, by the way, stands for address. So we can always tell that what we're loading is an object reference. It points into the heap. What? Yeah, it's loading this, because it has to. Because the only way that you can operate is to have this already on the stack, because the next line down, the get field, needs to have an object to operate on. Which object is it operating on? Well, the one that's on top of the stack, which is this. This is one of the shortcut forms that I mentioned earlier. Notice that A load 0 has no arguments after it, but load typically does. So this is a shortcut form, and the reason we do that is because it saves 2 bytes in the file size every time you want to load this onto the top of the stack, and you do that a lot. Now that might not sound like much of a big deal, but given that the first Java class files that I ever downloaded were over a 14.4 kilobits per second modem, I am very glad that I'm not paying an extra 2 bytes every time I want to load this. So we get the field, and then we return. So let's just see that in action. Load this on the stack. You execute the get field instruction to get that value, and back it comes. The setter method, we load 0, so we put this on the stack. We load 1, which of course will be the first argument. Basically, the order for local variables is this is 0 if this isn't a static method. The first local variable will be the first argument, if there are any, etc. And then basically your actual local variables for the method get shuffled up after that. We run the put field, and then we return. So let's see that in action. Load that up, put field, and now of course we have an empty stack, which means of course that we now really know what void means. Void, as we know, is not a type. What it actually is it's a statement about the state of the call stack when the method returns. Okay, and here's our constructor. Again, we load this, call the superclass constructor, and it's effectively become a void method for the constructor body. For object creation, we do something like this. So the way that we would call that constructor is with a piece of code like this. We call new to get some memory. We duplicate on the top of the stack. 2 copies of the uninitialized object are now on the top of the stack, and invoke special is called to run the constructor. And then finally we store in the local variable. The dupe is there because if you don't do it, the invoke special consumes what's on the top of the stack, and you end up with no reference to the object you just created, which means that you've just run the constructor body, allocated the memory, run the constructor body, and immediately made the object available for garbage collection. Unless, of course, you had side effects in your constructor, but you wouldn't do that, right? Okay, so we've talked about the stack. We talked about some bytecode. Another note just about the interpreter, really, it's the initial environment, and if you want to make your own implementation, interpreters are best thought of as just switches inside while loops. Hotspot actually is quite a lot smarter than that, but that would take us down quite a rabbit hole. So, let's talk about class loading. So, the class file is basically a binary metadata file, which is not really human readable, but it is parsable, and it's not that bad to work with. The overall anatomy looks a bit like this. You have what's called the magic number, which are the identifying bytes at the start of any Unix binary file. In Java's case, that's rather embarrassingly cafe babe. It was embarrassing 20 years ago, and it's scarcely got better with age. Immediately after that, you'll find the minor and major version numbers of the class file. There are different versions of the format, and it does change over time. The rules, for example, for Java 7 bytecode are quite substantially different for those in 6. But it's always backwards compatible because that's the Java way. I found myself having trouble remembering all of this, so I came up with this acronym, or mnemonic, to help me remember instead. And every time I see this, I always think of the movie Gremlins, because I don't know, it kind of reminded me of that. There's kind of like the gremlin cat on the right-hand side. Okay, so now we know what's in our class file, and it's basically the metadata we'd expect. What fields have we got? What interfaces? What are our methods? We need to get it into the platform somehow. So let's do some class loading. We add in a new live type. Notice that as it's being loaded, potentially it's going to be transformed. Lots and lots of frameworks do this, and we're going to do it too. So the first thing which happens when you class load is confusingly called loading. I don't know why the phase was called specifically loading rather than something a little more sensible, but there we are. It essentially reads in a byte array. That's normally on a disk somewhere. It might be over the network, and it does some very basic checks on the class. It basically makes sure that the constant pool, which is where a lot of the references to things that this class requires are kept, that collection of constants is self-consistent. But is no way does it produce a class object. And if you think about it, that's the process that we're undergoing when we do class loading. Is we start with a bunch of bytes, and we end with a live running Java class object that we can use. So we need to have that as our goal, our end point. And that, of course, may contain code. There may be static initializers for that class. At some point, that code has to run. But the way that the security model is designed, very much we want to leave the running of code until we're absolutely sure that it doesn't try to do anything evil. So the pointer arithmetic attack, for example, or any other of the huge number of things that could be wrong with the class file. We want to ensure that those checks have all happened before we start running any code. And the place we do that is the verification step. So essentially what this breaks down to is that the class file that is a candidate to be loaded is not going to do anything illegal at runtime. So things like, do you respect access control keywords? Right? Are you trying to call somebody else's private methods? Again, JavaOne won't emit code which does that, but I can write it. Do you have the correct static types for calling? Are you properly going to initialize your variables? All that kind of things. And for this verification, the stack nature of the JVM is actually really important. It's not impossible to do this on register machines, but it's a lot harder. The stack machine is actually fairly easy to reason about types for, and it's the checking of that at class loading time is one of the things that makes class loading interesting to us. There's a bunch of other things which happen, stack underflow, mismatch, all kinds of things. Any sort of clever attack which tries to subvert the runtime or the rules of the platform will be checked. You may need to load new classes. And so you may end up with a picture like this. I tried to load one class, object, and I've ended up with all of these other classes which are suddenly in scope and also need to be loaded. This doesn't actually happen for object because it's part of the core of the platform, and so it's actually loaded via a thing called the bootstrap class loader, which doesn't actually do any verification. It just loads it because essentially you have to trust something. Finally, after we've verified the class, we're ready to go. We can allocate memory for it. We can actually start to get ready, and then finally produce the class object, run the static initializers, and you're now ready to go. At this point, some aspects of the class are still not fully initialized. In particular, reflective aspects will be initialized lazily. So they won't be there unless you actually go and poke them. But the class object is fully usable at this point. So let's talk about some implementation details of how this is going to work, in particular the class loader. It's an abstract class. It works, but it has no abstract methods. So that probably sounds a little odd, but what it means is that if you want to use it, you have to subclass it. It can't be directly instantiated itself. It provides a public load class method for loading classes. You pass in the binary name and whether or not it should resolve it, and it will then load that class for you, which sounds great. But the other method, one which we potentially want to focus on a little more, is define class. Now this is a protected method. This is called from a subclass, and it's going to be the basis of custom class loading, and this is going to be our point that we're going to step in at. You probably know that class loaders form a hierarchy, where the class loader that loaded you is normally the one set as what's called your parent, and there's a delegation hierarchy where you try to let a class loader that loaded you deal with the class before you do. It's very, very easy to write a class loader. I mean, I'm missing a code comment here, but apart from that, that is a perfectly valid and usable class loader. Doesn't do much, but it's valid. Okay, so what are we going to do now? We've got the concept that we could use a custom class loader to somehow verify determinism. We also probably, therefore, need a library to help us analyze bytecode. I said the tooling space was very mature, and my library of choice is a thing called ASM. Hands up if anyone's used ASM before. A few people. Yes, it is not the world's friendliest of libraries. It's not got great documentation, but it's actually really pretty solid. You know, once you've got to know it a bit, it's fine. It provides a fairly close correspondence to the actual Java bytecode format, and it's kept up to date over many years. There's even a version of it hidden away inside the JDK. If you want to know how lambdas and so forth are actually implemented inside Java 8, go and have a look at the source code, and you will find a modified version of ASM lurking there. Don't use that one. Use an external library instead. The platform likes to keep its internals private, and you should respect that. So okay, so how are we going to use ASM? Well, there's a simple pattern which we can start from. You spin up a class visitor, you write out the header of the class, you generate any methods and constructors you want, and then there's a method to turn it into a byte array and write it out. If you want to know to dip your toes into the waters of ASM, I wrote an article which outlines the basics of it, which is available on InfoQ. How long have I got? Right. So this is the picture that we're actually going to have. We're not going to quite do as simple a use case of ASM as we saw on the last slide. Instead, what we're going to do is we're going to do a transformation. We're going to load in the class file as a byte stream using define class, pull it off the disk, run it through an ASM process to determine whether or not it is actually deterministic, and then we're going to output some potentially modified code. Okay? So now we get to the real meat of the talk. Let's talk about provably deterministic execution. How am I going to get around the halting problem? Well, here's how you do it. First of all, at class loading time, anything which is non-deterministic, which means anything which tries to create another thread, anything which calls a method like current time millis or nanotime or anything else which I know is a non-deterministic method, I'm just going to reject straight away. Okay? And after I've done that, I'm left with a set of methods that may, and a class which may possibly be deterministic. Now, the only problem is that it might run out of resources. It might be in an infinite loop somewhere. So we can't have that. So what I'm also going to do is I'm going to rewrite the bytecode, and I'm going to insert resource tracking code into the candidate program. Okay? And then at that point, I'm going to allow it onto the platform. Then at runtime, if anything happens which is going to breach resource limits, that contract is killed. And now all we need is a transaction monitor. Because then at that point, I can roll back the effect of whatever the contract did to the previous state. And I should have a system which is actually robust enough for deterministic execution. Should we see how it works? So, okay, the whitelisting class loader. There are a few Java keywords that I've highlighted here of being of potential interest. Okay? They are catch, because we might try to, for example, catch the kill signal I'm going to send to contracts. I could use thread.stop to kill off a contract that's breached its resource limits, but we know that thread.stop is bad, so we don't do that. Instead, I simply have a method which will throw a thread death error. Now, someone, enterprising person, might try to catch that thread death error. So that can't be allowed. So I have to go through the code and look at any catch block and see if anyone, when loading, if anyone tries to throw thread death or catch thread death or throwable or anything on the path between the two, that contract is disallowed. So I have to check for that. Native, yeah, no native code. That's probably not a surprise. So anything which declares a native method, that's out as well. Synchronized, I think I have an edge case. I haven't been able to find a test case for it that I could actually deadlock with suitably nasty synchronized. Either way, I'm just, there's no point because the contract should be single-threaded. So we'll just get rid of synchronized. So what that will mean is that the monitor enter and monitor exit bytecodes. So how does the monitor enter work? Well, you put the object whose monitor you want to lock on top of the stack, and then you execute monitor enter, which consumes that, and similarly when you want to exit the monitor. So I'm just going to rewrite monitor enter and monitor exit to pop. You put the object on top of the stack, great. I'm just going to pop it off. I don't care what it was, and I'm certainly not going to try to do any locking. Transient is ruled out for complicated reasons to do with serialization, I shan't go into. Strict FP, hands up if you've ever written strict FP in your entire life. Nobody. That's normally the answer. I have used it once. The thing about strict FP is it says follow precisely, strictly, the floating point semantics of the IEEE 754 standard, which is the floating point standard. If you don't have strict FP on your method, the hardware will use better precision if available. That obviously is a potential source of non-determinism, so we enforce strict FP on every single method we ever touch. And now, the demo. This, of course, will not work because demos never ever do. Okay. So here is the whitelisting class loader. Is that too small? Should I increase the size of the font? Yeah? Okay. How's that? Cool. Okay, so this is the whitelisting class loader. Sure enough, as promised, it's a class loader. And inside it, I'm going to keep a couple of things. I'm going to keep a map of classes that I've loaded, and I'm also going to cache the bytecode which in its transformed state. I've got additional search paths because the classes that I'm going to want to load probably aren't on my class path. So I've got to maintain a separate internal class path for that. I've got a thing called a Candidacy Status. This is a domain object which determines whether or not the object actually is deterministic. And that's used for a modified version of, well, what I subsequently realized is actually a modified version of Dijkstra's tricolor marking algorithm. It's not quite the same, but it's very, very close. I didn't tell you about this. This class loader actually has two modes. The first mode rejects anything which is non-deterministic. The second mode strips out any non-deterministic methods and keeps only the deterministic part of the class. Okay, why did I build that? Well, because I actually want to have some useful classes. Java util, Java IO, not Java IO, Java util, and Java text, certainly. So I have actually built a deterministic version of a subset of the Java collections library. By running the class loader repeatedly over the same packages, I can build up a larger and larger map of things which are known to be deterministic. Because the way that the algorithm is going to work is, if I have written you on a list, a special whitelist, to say that method is deterministic, then any method which obeys all the other rules and calls only deterministic methods is itself deterministic. So on a recursive set of calls through the same packages, I will eventually reach the point where I've iterated so many times that the input set and the output set are the same, and I know what my set of deterministic methods is. At that point, I can save that as a list, and the next time I fire up, I don't have to do that repeated walk. So that's what remove non-deterministic methods means. Okay, 5 minutes. So we've got a bunch of constructors here. Where this actually, the real meat of this is find class. And find class basically is what you actually override when you write a class loader. Load class is the entry point, but that will delegate back to find class. And if you look at the source code for class loader, let's find class. You can see that if you don't, when you're subclassing class loader, if you don't override find class and actually provide an implementation, you get a class not found exception. So that's basically the fallback, and that's actually where you put the hook for your own class loading. Okay, so how do we do this? Well, the first thing we do is we check to see if we've already loaded it. If we haven't, we change its name, because of course, if I'm going to use Java util or Java text, then I can't use those package names, so I have to change them. So in fact, what I do is I rewrite the package names on the fly as well to bring them into what we call the sandbox. So if they're already in the sandbox, great, we'll use that loaded class. If not, we'll try and let the superclass find it, so that if it's something that's already present on the platform which is being used, then it can be found. If not, well, then it's Argo. And what we do is we pick up the method. We set up our ASM class reader. From that, we also set up a whitelist checking class visitor, which basically is where some of the work starts to happen. So here, for example, this is the visit method. ASM is based on a visitor pattern, which means that you get callbacks into individual methods that you've overridden here. So here, for example, is me forcibly switching on strict FP for every method. Here is me immediately saying, if you're native, then out you go. This is the finalize check. No finalizers either, of course. And then at the end, when we visited all the methods, we finally call visit end, and we basically run this algorithm to determine whether or not we're deterministic based on what we call. Okay? There are method visitors somewhere else as well. I'll just show you. I think I've just done something wrong. There we go. In the method visitor, I've got a bunch of stuff to do with the try catches. So if I try to catch thread death, away it goes. If I try to do anything which involves invoke dynamic, again, you're kicked out. And here's where I set up the other piece for the determinism state of this method. Okay, 2 minutes left. What I did, in order to test all of this out, is I wrote myself a basic contract container. It's called Grey Malkin. I don't know where I was going with that. Grey Malkin is a witch's cat, tomcat, something like that. I have no idea what I was thinking. And basically what this does is it starts up a thread which watches a directory for incoming classes, and then it tries to load them into a contract. So where's the other one? Yeah, here we are. So we pull things off the out the directory and load them if we can. The way that this is handled is we have what's called a contract class, which basically is a representation of a running thread with a contract on it. So it's one thread per contract. It's and there's an executor which basically which runs the actual contract. I didn't have time to implement a full distributed ledger, so what I did was I produced something to be mocked up to look like it. It's called a vetted log appender. It just appends to a log, and it won't allow you to do that if you're non-deterministic. So the appropriate interface is string returner, so my contracts have to implement string returner. So let's run this. Okay. So here's one I made earlier. Oh, and I need a... Okay. So in here, I'm just going to tail the log. We're waiting for stuff to turn up. Actually, let's move that into a separate window. So we've got some classes in here. Let's send one of them across. Simple one.class into the test directory. And as you can see, a bunch of stuff has happened. It's gone and it's checked through this to ensure that it's deterministic. And I didn't have time to tell you about the runtime cost accounting, but all of that code was inserted into the code. And now this time, if I pass in, is it 3, which is non-deterministic? Sure enough, it's gone through. Class simple3 cannot be loaded because it's calling a non-deterministic method, and so it is not allowed into the sandbox. Okay, I think my time's up. Does anyone have any questions? Yeah. Okay. So the resource. Yeah. Okay. So we can do that. So it's basically in the costing package. There's a thing called a runtime cost accounter. And the way that this works is it has 4 thresholds. So an allocation threshold, because I've rewritten new to put in code which will show up if you try to use too much memory. A jump threshold, where if you try to loop too many times, it will kill. And an invocation threshold as well. If you want to come and talk to me afterwards, very happy to tell you more about the research. The work was originally commissioned by R3. It's part of the Corda project. There's another article about it on InfoQ. There are a bunch of books that I wrote, and thank you very much.